Hi, welcome to 221. Today we are going to look at a worked example of using the three-dimensional force calculations that we developed in the earlier lecture class. Okay, so before you get started, get a pen, notebook, calculator and ruler ready. Put it beside you. If you don't have that, pause this right now, go get it and come back. Okay, so the idea is, while I do it, I want you to do it with me. Okay, so it's just like what you might or what we are expecting you to do in a lecture in a classroom. Okay, now the nice advantage of doing this online is that you can actually pause and catch up with me as I do. It's not easy to do that in a classroom, but in a setting like this you can do it. So please make use of that. Think of it this way, it's like singing along. You know what I mean? You learn by singing along with somebody. So I want you to sing along with me. Think of it like your own private karaoke, but you're writing it on a piece of paper. Okay, but you know what I mean, right? So please do that. It will help you a lot. I know how it works. So just go ahead, get all the stuff, sit there and do it, and you will learn a lot. Okay, very good. So now let's start. Okay. Yeah, okay. We are going to talk about things which are called guy wires. Can you see this word, guy wires? A guy wire is actually a wire that is used for stabilizing tall structures. Can you see this tall antenna? And I don't know whether you can see it, but I'm hoping you can see these wires that come out of this antenna. It's used to stabilize these things. If you build your own wind turbine, for example, a small windmill, for example, you have to put these guy wires because the wind is going to blow, right? And when it blows, it's actually going to try to topple this windmill over. I mean, that's the whole point of having a windmill, right? You want the wind to blow, but the wind puts a lot of force on the top of the windmill and it will topple over. That's why you have this complex arrangement and these guy wires to make sure that the whole windmill doesn't fail. Okay, remember structural safety, right? So that's a very important thing. And there are 4 guy wires. Another interesting example where guy wires are used is in overhead power transmission lines. You can see this now. So what happens is, in places where there is a change in the conductor's direction. So the power transmission line comes like this and there is a line change. Then you have to do a guy wire. Otherwise things will fall. Or, nowadays they are actually doing very, very big poles which can withstand it sometimes, but it's a simple device is to put a guy wire. In fact, any tall structure, for example, if you want to set up a tree, for example, you'll have to use a guy wire. Okay, so this is a fairly common thing. What we want to be able to do is find out how much force you can put on the guy wire. The guy wires have to be pre-tensioned. That is, you're gonna put some pre-tension or pre-force in it so that they are all going to pull on these cables. I mean, on these poles. Right? So I want you to understand that a guy wire can only pull, it can never push. Right? It's like this. If you have a thin wire like this, you cannot push on a string, no? It will collapse. But you can pull on it. So I want you to understand that all wires, the advantage is that you know which direction the force is going to act. At the place where it is connected, it will always pull. So let me write this down because this is a very important idea. Wires will always pull at the points where they are connected. Okay, they cannot push. That's a very important point about guy wires. Okay, excellent. So we now got the idea. So now what we have to do is figure out how much force these guy wires are actually applying on the poles. Now, why do we care about that? Because tall slender poles, if you apply too much compression force, that is, if you apply too much force that is going to squeeze these things, they will collapse. So your guide wire, you cannot go on tensioning it. If you tension it, it will suddenly buckle. So you got to make sure that there is some good tension to the wires. At the same time, you got to make sure that things work out well. Okay. So let's look at an example problem. This is a toy problem just to get us going. Okay. So before we go into the example problem, I just want to make a quick survey so that we are all sure about what we are supposed to do. Okay. So remember, our typical situation is where I have a force F, there is the force, okay, and it's along the line joining A and B. I know the coordinates of A and B. The coordinates are known. I'm going to put a tick mark here saying that I know the coordinates, right? So what I need to do is first find the line vector, and the line vector, so what I'm going to do is I'm going to take this force and I'm going to try kind of draw it. So the line vector points in the same direction of the force, and it is LAB. That's a line vector, and the unit vector is this blue arrow, and that is line vector divided by length of the line vector. And our notation for our forces is going to be, this is magnitude, that's the direction. So I want you to understand that in our notes, whenever I use the word direction, I always mean some unit vector, okay, which tells me which way to go. That's why it's called direction. So when I say magnitude and direction, it means the scalar times the unit vector. So that's how you should think about it, magnitude times direction. So that's the best way to quickly translate English into equations. Okay, so I told you, pictorial to vectorial. Okay, so just to remind you, the unit vector is line vector divided by line length. Please memorize this. Please memorize this so that you don't forget. And the line vector always goes from tip to tail. So I got to subtract the tip, that is B, minus the tail. Okay, how do I know which is the tip and which is the tail? The direction of the force vector tells me which is the tip and which is the tail. So I just want to make sure we are all on the same page. Okay, excellent. And please memorize this. Okay, so here's the problem. So please read this. I'll give you a few minutes to take a look at it. The guy wires are used to support an antenna. So this is the antenna. Under the current wind conditions, the tensions are FAB equal to 800 newtons. So this is 800. FAC is 600 newtons. So this is 600 newtons. And FAD is 750 newtons. This is 750 newtons. Okay. Now tells you the magnitude. What about the direction? Well, remember what I said. At points of contact, a wire can only pull. So at this point of contact, this wire can only pull. This point of contact, the wire can only pull. This point of contact, the wire can only pull. The situation is different here because, here at these points. Okay, because that's a different point of contact. We're not worried about it. We are only worried about what's happening to the antenna. I don't really care about what's happening to the ground yet. Okay, the problem is I want the antenna can take only 1300 newtons of compression. So compression means squeezing force. Which way will that be? So the antenna can take only maximum 1300 newtons. So remember, I wrote less than 1300. Okay. So that's our condition. The question is this safe? Okay. So we are off. Here is the pictorial. We are going to convert this pictorial into a vectorial, and then we will do our usual calculations. Okay. So let's get started. Okay, before we start, as usual, strategy. Our higher order thinking skill here that I want you to learn is to break up the task into manageable procedures. That's the higher order thinking skill here. Okay. So let's look at it. So task number 1. What do we have to do? We have to convert. So I'm going to write this one. Find force vectors. That's task number 1. So can we do it? Yes, we can. So how do we do that? I need to know the magnitude. And then I need to know the direction. So this is known, this requires calculation. Okay, so that's how we do this. This is a procedure. Then task number 2, sum the vectors. Why? Because I am interested in finding the net force. And this is a very simple task. This is just vector addition. Right? And then task number 3. Find component in direction of interest. That's task number 3. Okay. In our case, the direction of interest is pointing down like that. That's the direction in which I am interested in. So I got to find this out. Okay. Now this requires, what do I need to know how to do? Whenever you see component, I'm going to say dot product and direction of interest with unit vector. And we are going to do this 3 tasks. So think about it this way. So it starts out first task, then each task corresponds to a procedure. So if it turns out that this itself is a challenge, we break that up into sub procedures and so on. Okay, that's the higher order thinking skill you should learn. Very good. So we got the strategy down. So off we go. Let's do this. I've written all the numbers out there, so you know what is what. So let's go and figure this out. Okay, now we are at the details. So let's start with task 1. Forces. Magnitudes are already known. 800 newtons, 600 newtons, 750 newtons. I need to calculate directions. So need to find EAB, EAC, EAD. Okay, so in order to do that, I'm going to write down the position vector of each of them. What's the position vector of A? Well, X component is 0, Y component is 0, Z component is, height is 25 meters or 25. Okay, what about B? Let's see. For B, X component is 0 because this is the X direction, Y direction, Z direction. So for B, X component is 0, there is no X component. Y direction minus 17, it's in the negative Y direction, so minus 17, Z is 0. And C, let's see, X component is 25, Y component is 12, Z component is 0. And for D, X component is minus 15, sorry, X component, yeah, that's right, minus 15. Y component is 12, oh sorry, 10, that's this distance, and Z component is 0. Those are the A, B, C and D. So first thing is I need to find the line vector LAB. I hope you are actually doing this along with me. If you are not, it's not helping you as much as you think it will. Okay, so please try it. I mean, humor me, just try it, you know, it'll work. LAB is B minus A. Why is it B minus A? This is tip, this is tail. So this turns out to be, I'm going to write it down, LAB turns out to be 0 minus 17 minus 25. and its magnitude, that is the scalar LAB, is 30.2 meters. I'm going to keep 3 significant figures throughout because that's all I'm going to need, right? So let's do the next one. So what I want you to do is you try doing the other 2 and then you can see whether you are getting the same answer as I am. That's the best way to do it, okay? So pause here, try it out, find LAC and LAD, these 2 vectors. You find it out yourself, then come back and tell me whether you got the same answer as I got, okay? So in my case, this is C minus A, which turns out to be 25, 12, minus 25. So LAC, its magnitude turns out to be 37.3 meters. LAD turns out to be minus 15, 10, minus 25. And LAD is, let's see, it turns out to be 38.8 meters. Whenever I look in the side, what it is that I have calculated these things, no? So I'm making sure that I'm writing the right numbers. Okay, so that's LAB, LAC, LAD. Excellent. Now let's calculate the unit vectors. Okay, and this turns out to be EAB equals LAB divided by LAB. If you do this, you will get 0 minus 5.62. Oh, excuse me. Well, here's a good check. How do I know it's wrong? You know that, right? There cannot be more than 1. Because the product, I mean the magnitude of all of this has to add up to 1. 0.562 comma minus 0.827. EAC LAC divided by LAC, which turns out to be 0.670, 0.321 minus 0.670. EAD LAD divided by LAD, which turns out to be minus 0.487 0.324 0.811. Okay, how do I know whether these unit vectors are correct? What kind of diagnostics can I run? Well, look, if my line vector has 0, then my unit vector will have 0. That's check number 1. The sign of the line vector and the sign of the unit vector have to be the same. So this has to be minus. Okay, so there, you see how I got that error? Because the signs have to be the same. Okay, so if it is 25, 12 minus 25, I got to have plus, plus, minus. So minus, plus, minus, you should give me minus, plus, minus. Also, roughly speaking, if 2 of them have the same magnitude, the corresponding unit vector will also have the same magnitude. Can you see 25, 25, 0.67, 0.67, right? And roughly speaking, the ratios will be the same. This is about half, that should be about half. You're with me? And this is slightly bigger than this, so this has to be slightly bigger than that. So all of these things are quick checks. Now that we have the unit vectors, finally we are going to do forces. FAB equals FAB times EAB, which turns out to be up to 3 decimal places, 0, minus 450, not 3 decimal places, up to 3 significant figures, and then minus 662. And this is in newtons. You can do the same thing for FAC. (402) 193 minus 402. 402 193 minus 402. And then F A D E A D equals minus 365, 243, minus 688. What kind of checks can I do to make sure it's correct? Same thing. If my line vector has 0, my force vector had better have 0. And the sign of the line vector and the sign of the force vectors have to be the same. So 0 minus minus means 0 minus minus. So plus plus minus, plus plus minus, minus plus minus, minus plus minus. Okay, and then you can roughly see ratio has to be double. For LAC you can see that, and that ratio has to be roughly double. You see what I mean? And then this one has to be bigger than that, and this one has to be bigger than that. All those things are roughly correct. So you can think, okay, chances are I have not made a mistake. That's the point about doing the royal route. You see what I mean? I can actually backtrack and make sure that we are fine. So task 1 is done. So now let's go to task 2. Sum all the forces. This is the easy thing to do. This is not a huge problem. This will turn out to be 37 minus 14 minus 1671 newtons. So what does that mean? The net effect of all these forces on the pole. So here is the pole. Okay. So let me draw this force and you will see what it means. Okay, the X force is 37. So I'm going to draw something like that. That is 37 newtons. And then Y force is minus 14. So remember, that's half of that. So that's minus 14. And then Z force is 1671. Minus 1671. And this is going to be. So I'm going to draw it roughly to scale so that you can see what happens here. (14 newtons) is roughly a small bag of apples. You know, I told you 1 Newton is an apple, no? So this is very small. This is actually slightly larger, but still, I mean, nothing that you cannot carry. Now, this is 3 people, maybe 4 people. Yeah, maybe 3 people standing on the pole. Here. Like that, you know, just so that you get an idea of what it is. This is the force which is likely to cause the pole to fold up like that. If that happens, it's over. And the question is, how do we find it? And in this particular problem, it's easy, but I'm going to do it by the royal route, which is I'm going to take the royal road even though there is a shortcut. So I'm going to do the last step, task 3. Find component. The force itself was, let's see, 37 minus 14, 1671. Direction is minus k direction. Can you see? That's this way. Which is 0, sorry, minus 1671, 0, 0, minus 1. So F dotted with minus K equals 1671 newtons, which is more than 1300 newtons. You remember what is this 1300 newtons? That was the max force. So this is the demand, sorry, this is the demand, this is the supply. And you know, demand exceeds supply, problem. So it's going to collapse. So you can say, look, this is dangerous. We got to do something about it. Okay, now let's first see if our answers are roughly correct. Okay, so I want to make sure that it is somewhere, it's not 10,000 newtons and it's only 1600 newtons. How do I make sure of that? Remember, all these poles are pulling down, right? So I know that the force has to be less than, as if they were pulling down vertically. That is 800 plus 600 plus 1750 plus 750. How much is that? 800 plus 600 is 1400 plus 750. So it has to be in the order of about 2150. That's a very crude estimate as to what you should get. And if you look at the forces, you can say, look, if you look at any other direction, two of the forces are in one way and the third one is in the other way, so you are likely to get things cancelled out. And sure enough, the other two forces are pretty small. Okay, so this is a quick way for you to check. Okay, 2150, I am at 1671, probably I am not too far off. Okay, so this is your check for stink. What do I mean by stink? You know, if you got 150 newtons or 15,000 newtons, how do you know whether it's correct or not? You just do a crude check, and learning how to do crude checks is a higher order thinking skill. Learning how to check things on the fly is a higher order thinking skill. So remember, when we actually calculated the unit vectors, we checked whether roughly the magnitude, the ratios were correct, and we checked whether the signs were correct. Those are simple higher order thinking skills, and I want you to practice them every time you solve these problems. You will then catch most of the errors. Thank you very much.